So we are very happy to have Zhenbin from Stanford, and he will tell us about the replica wormhole, page curve, global symmetry, and remnant. Please start.
Okay, thank you, Masamichi. It's a great honor to talk at Berkeley. Today I'm going to talk about replica wormhole and its connection to page curve, global symmetry, and remnants. So, since the discovery of black holes, black hole has been a very important playground for testing ideas about quantum gravity. Understanding black hole can help us perhaps understand our own universe about cosmology and also the singularity of the black holes. And recent years, there are a lot of development that we achieved in understanding black holes. And it's also related to other areas such as strange metals, quantum chaos, quantum information, and the random matrix theories. And throughout those studies, one important idea about black holes has been used. That is what's now called the central dogma of black hole. It says, just seeing from outside, a black hole should be treated as an ordinary quantum system with finite degrees freedom. The number of degrees freedoms is given by the Bekenstein-Hawking entropy formula, the area of horizon divided by 4G Newton. And in addition, it should evolve unitarily under time evolution. Today, I'm going to give evidence of the first part of the central dogma from low-energy gravitational path integrals. So this central dogma is essentially what we have keep being using in the holographic systems. But actually, this central dogma is have a lot of puzzles or tension with the semi-classical description of black holes. The first puzzle is when we consider to entangle a black hole with matter field. In the geometric picture, such entanglement entropy can be bigger than S black hole, simply because you can entangle more and more quantum fields inside of the black hole interior. But for a black hole, if for a quantum mechanics system with finite degree of freedom, this cannot be true. As most of you know this familiarly, that is one of the black hole information paradox, where we consider forming a black hole and let it evaporates. In the classical picture, it describes an evolution process from pure state to mixed state. And moreover, the initial the information of the initial state remains inside of the black hole. If we draw the entropy of the Hawking radiation based on the geometric calculation or semi-classical calculation, then the entropy keeps increasing. But due to the evaporation of the black hole, the Bekenstein-Hawking entropy is decreasing. So based on this, in order to be consistent with the central dogma, for example, then Don Page famously argued that the actual behavior of the von Neumann entropy of the radiation should obey the Page curve. At early time, the radiation system is smaller than the black hole system, so it can get as many entanglement as it can. But at a later time, the maximum entropy or the maximum entanglement it can get will be bounded by the black hole entropy. So it should goes down. And also recently, there are understanding of this Page curve from using holographic RT formula. If we think about the main keys of this problem, of this why we have this tension at after the Page time, then one finds that the main keys of the problem is actually a state counting problem. That is, at the latest time, in Hawking's calculation, we have so much entropy because the radiations are entangled with a lot of interior Hawking partners. Here I draw illustration of the Hawking partners, and at a later time, the interior volume of the black hole grows, and so you can have more Hawking excitation inside of the interior than the Bekenstein-Hawking bond. Let me say it in other way. Consider just an old black hole. Then, as you look at the black hole at a later and later time, the spatial volume inside of the interior grows with time. It grows without any bound. And if you consider you put some QFT in this background, then the degree of freedom of the QFT, which is extensive, can be much bigger than S black hole. And in the late time of the evaporation process, we have the same issue that we have a lot of interior Hawking partners to entangle with the exterior, and in particular, the degree of freedom that described by the semi-classical picture is much bigger than the black hole entropy. And so this is much bigger than the black hole entropy. Very natural conclusion will be that those semi-classical states must be overcomplete. Those semi-classical states must form an overcomplete basis such that the actual Hilbert space dimension is given by e to the S black hole. A related issue to this state counting problem is this remnant problem. The remnant argument for the no global symmetry in quantum gravity, where you consider about gravity coupled to a QFT with some global symmetry G. And you create a black hole by forming a matter field that carries some representation R under a global symmetry. For simplicity, let me assume that this global symmetry is non-abelian, so that the dimension of the representation is non-trivial. Now you consider evaporation process to evaporate to a small black hole, such that the Bekenstein-Hawking entropy, the entropy of the black hole is smaller than log of beam R, where R is the representation. In other words, you form a remnant. Then there will be simply too many states due to the global symmetry, because the global symmetry will require those beam R requires a super selection sector in its representation. Then it will require minimum of the dim R states, but that will be bigger than e to the S black hole. So a resolution of the puzzle 2 will naturally lead to a violation of global symmetry in quantum gravity. Actually, in the earliest, in the original paper, in the Banks-Seiberg paper, they trying to use covariant entropy bound to argue this, but later the covariant entropy bound was proved purely assuming the QFT plus gravity. And so I think modification of the argument should just use the central dogma to argue that global symmetry must be violated in quantum gravity. So those are the 3 puzzles, and I'm going to yeah.
Which proof are you referring to here?
Which proof? The proof you gave, right? So you're right with Juan and Cassini.
With Juan and Cassini and Fisher. That proof applied only in the weak gravity limit. So so that would, I don't think that proof would apply to this particular setting.
Oh, really? But
it would apply in a setting where you can do vacuum subtraction to to define the entropy, which here you can. So somewhere, so if you're near some fixed background, usually Minkowski space.
Okay, well, I thought here if you are trying to just using the covalent attribute bound, I will just working on the light sheet like locally at here. If say I look at time.
Yeah, no, that is still a conjecture.
Okay.
Yeah.
Oh, okay. I thought you guys approved prove this.
It would
okay,
be kind of boring if we'd been able to prove it completely. Yeah, that would be. We mean that there's no new information in it. Yeah.
Oh,
anyway,
okay.
Sorry, this is not very important, I think, for the rest of us.
Okay, so I take that back. So maybe a covalent attribute bound can also be used to argue that there's no global symmetry. But here, definitely the central dogma that the black hole can only describe e to the s black hole states will prohibit you have any global symmetry in quantum gravity. And the talk will be using Replica Wormhole to resolve all those puzzles. I mean, at least to my standard. For the first puzzle about there are too many entanglements between radiation and black hole, then one can directly calculate the von Neumann entropy. And I guess most of you are very familiar with this. One simply consider calculating the von Neumann entropy of the radiation that entangle with the black hole. So at the common rule, you're using replica trick to calculate the von Neumann entropy, and when calculating the replica path integral, you need to consider about n copies of the gravitational system due to this trace rho to the n, and then when you do gravitational path integral, there will be non-trivial gravitational saddles called replica wormholes that dominate this entropy calculation at late time. And as a result, this gives you entropy that saturates the black hole entropy. Entropy of the radiation that saturates the black hole entropy. At the early time, this replica wormhole geometry is not dominated. So you only have fully disconnected geometry dominate. That is the same as the original Hawkins calculation. So you get the same result as Hawkins predicted. And in the middle, there's the first order phase transition. To talk about the second puzzle, that there are to talk about the state counting problem, that there are too many states, too many semi-classical states. Then a strategy I will use is just directly construct the minimum basis out of those semi-classical states. So we will find a minimum basis of states I, such that any other excitations inside the black hole interior, let's call it psi, can be reconstructed from the states I. And more precisely, I will show you that the number of states, semi-classical states you need to use is given by e to the s black hole. In other words, you just need to choose out of those large number of states, e to the s black hole states, e to the s black hole semi-classical states, and that can be used to reconstruct any other excitation inside the black hole interior. In other words, those expand the Hilbert space of the black hole interior. And in particular, those states have no particular restriction on this basis. It could be firewall states or non-firewall states, and there's like large redundancy. So here's the cartoon. So maybe the afferent is a firewall state and the answer is non-firewall states. Then you can reconstruct between them each other. To do the puzzle 3, so since those choice of states I does not have particular restrictions, it can carry different global charges with a state per psi, so that global symmetry is not conserved. Simply, they have no superselection sector. And moreover, I will also tell you that the Replica wormhole, the wormhole will also predict a more direct consequence, like observational consequence of violation of global symmetry. That is, it will give rise to a non-trivial scattering probability between different charge states. Why is that? Well, in the usual QFT course, we used to focusing on scattering amplitude because the scattering probability is just a square of it. But when you consider about gravity, things evolving in gravity, the scattering probability and the scattering amplitude may be a little bit different. And since when you look at the scattering probability, you have effectively two copies of the system. And then there could be new gravitational saddles connecting these two systems. Well, yeah, and I will comment on that later. Is this clear? Okay, so if it's clear, then let's move on.
This last part is what you're going to discuss in more detail in this talk? Or?
Well, I'm going to discuss the more detail in the second and this state reconstructing and this part, these two parts. Yeah.
Yeah, that's what I meant. Yeah, this part of the three. Okay, thank you.
Well, yeah, but this part is the second part, right? The state reconstruction. Yeah. Yeah. First, let me explain the main ideas in a extremely simplified gravitation model, but it can be extended to more realistic models. This is this Endofwar brane model, where you consider simplify this evaporation process to a thermalization process. That is, you couple to a you couple to a bath that have the same temperature as a black hole. So here you have a flat-based bath with same temperature coupled to a ADS black hole. And here this red arrows and blue arrows labels entangled Hawking pairs, interior modes and exterior modes. And then another level of simplification is to simplify the radiation to qubits, and then simplify the interior modes as excitations on Endofwar brane. That is just used to describe single-side black hole. And the three statements I'm going to talk about in this model will be the following. The first, of course, is that the von Neumann entropy of the radiation saturated to S black hole. The second is that on this Endofwar brane, you can manually increase the species of the brane excitations, and in particular, it can be you can increase it such that it goes beyond e to the S black hole. Then, in that situation, we will see that those states will form over complete basis, so to reduce the Hilbert space dimension. And the third part is that in this model, to see how global symmetry is explicitly violated from Replica wormhole. So let's consider. Let's introduce some notations for this model. So first, let me first review the page curve calculation, because maybe some of you are not familiar with that. So we look at this entangled state. We can denote this state as sum over black hole state psi I entangled with radiation state I, where psi I denotes the black hole state with brane excitation in a state I. And in particular, it has Euclidean preparation drawn at the left-hand side. In terms of boundary description, then we have this state have a single asymptotic boundary, and then ending on an Endofwar brane with brane index I, which labels orthogonal states living on the brane, and then it's entangled with the radiation. And the gravitation path integral rule I'm going to use is the following. We would we will fill in with all of the smooth geometries that are compatible with the boundary condition. Like in general, when we do gravitation, when we do path integral, we have input and output. When you do the gravitation path integral, the input is a boundary condition plus the action, because you cannot specify the bulk metric. And the action we will take will be just topological action that only counts the topology of the bulk geometry. And the output will give you all smooth geometries that are compatible with the boundary condition. So if the boundary is a circle, then the smooth geometry, bulk geometry will be a disk. And if the boundary is a semicircle, then the bulk geometry will be a half disk, which ends on an Endofwar brane, which is this blue guy. And moreover, if you have two semicircles, then you have two types of geometries, two half disk or a disk. So that is the rule I'm going to use in gravitation path integral. And the quick notation, the Berkeley-Center entropy was given by the disk path integral. So S black hole is given by the coefficient of the topological action in 2D. So, so quick review of the entropy calculation. We can do Hawking's method. So we, as usual, we look at the, first we look at the reduced density matrix of the radiation. So we have the inner product of this, we trace out the black hole system. So we get inner product of psi and psi j. In terms of boundary description, that describe a single asymptotic boundary ending on, beginning from a brane at flavor I, ending on brane with flavor index j. And after doing the gravitation path integral, you got the smooth geometry with a single brane connecting these two boundaries. And that gives you, since the I and j are orthogonal states living on the brane, that is proportional to that ij. So you get get to this maximum entangled state of the radiation, and you get the naive entropy log k. And but if you look at the purity of the system, you look at trace rho squared, then it contains two copies of system. That is two semicircles. And if you fill in with the gravitational path integral, then you have two geometry dominates, one corresponding to two copies of the original system, and the other corresponding to a wormhole connecting these two black holes. There's two boundaries connected. Yeah.
I agree, of course, with what you are describing. I just want to emphasize, and I wonder if you agree, that normally, if we have a consistent description, a quantum description of a system, these two methods have to agree.
Yes.
And there is nothing obviously wrong with the first method, Hawking's method. So yes, while I think it's remarkable that we now have a gravitational path integral way of deriving what we think is the correct answer, I don't think that's the same as saying that we've resolved the problem, because we still don't understand why Hawking's method gives a different answer. I mean, that should not happen in a consistent theory.
Yeah, well, that I will say we still don't know the answer of the factorization puzzle, and I will discuss it just in the next slide. Okay, just so let me go over this calculation. So when calculating trace row squared, we're summing over the index I and j. So the first geometry gives us a single index loop. So after normalization, we'll give you 1 over k. And the second geometry gives you 2 index loops. And so the k factor of k cancels, and the ratio gives you e to the minus s black hole. And so clearly, when k is larger than e to the s black hole, then the purity saturates to e to the minus, saturate to e to the minus s black hole. Therefore, the second running entropy saturates to s black hole. So if you're using this rule, then there's no paradox. And you can also generalize this to calculate the von Neumann entropy by looking trace row to the n and taking n goes to 1. But I'm not going to talk about that. As Raphael addressed clearly, there's a tension between this first approach and the second approach. And in a true microscopic UV complete theory, then these two approaches should give us the same answer. That I will describe as this following factorization puzzle, where if we look in the first approach, we directly calculate the matrix element of the reduced density matrix, the psi I, psi j, which is given by psi I, psi j. So in the product of two semi-classical states, two gravitational states, and that gives us 0 answer, because in this simple gravitation path integral, all the smooth geometry contribution give you 0 if I and j are not equal. But when we do this this running entropy calculation, we're looking at psi I, psi j squared, and that gives us a non-zero answer due to the existence of the wormhole. And so if we have a single theory that we have UV complete theory, then one can speculate that maybe the actual answer is that the psi I, psi j is actually given by some non-zero inner product. That's called Rij. And the rule, the gravitational path integral rule we are using is giving an ensemble average result. Anyhow, we don't have so many parameters in our path integral. We just have single S naught. How could we get such a, if I and J are they run from 1 to 1,000,000, how could we recover like such a big different numbers, right? So so the philosophy I'm going to take is that maybe simple gravitational path integral only give us ensemble average result. And that means if we try to talk about some quantum mechanics physics about like Hilbert space dimension or entropy of the system, we need to be more careful. We must not be cheated by the by a single gravitational picture. We need to like looking at more complicated object and using gravitational path integral. In other words, we should looking for ensemble average result. We should looking for results that self-average, and then we can trace the gravitational path integral. Okay. So, but the key lesson here I want to say is that this gravitational path integral do give us a strong prediction. It predicts that naive semi-classical orthogonal states actually have non-zero inner product. And using gravitational path integral, we got some information about this inner product. Any question? So the fact that this naive semi-classical orthogonal states have non-zero inner product means they can form over complete basis, and then we may construct some question that is self-averaged, so we can use gravitational path integral rule to investigate the answer. For example, the number of the dimension of the Hilbert space is a self-averaged quantity. I mean, it's just one number, so we can use gravitational rule to calculate, ask it. And here we will the procedure approach we were going to use is consider a basis of semi-classical states that labels different in this Endofwar brane model. Those are corresponding to different brane excitations. I run from 1 to L. So in total we have 1 to K states, much bigger than e to the s black hole. And out of this K state, we choose L states, L different states. And we're going to ask whether any other states, A, lying in the complementary Hilbert space, can be reconstructed from those states I. That is, can we find a coefficient Fi such that any state A can be decomposed as a linear superposition of states I? And if so, what is the requirement on this basis I, and also the number of the states L? That question can be answered by looking for the maximum inner product between A and this superposition of states. You're just simply looking for the inner product between A and the summing over I, Fi times I, and looking for the coefficient Fi to maximize this inner product. And in general, you'll find that the maximum inner product you can achieve is given by coefficient Fi that is equal to this formula. This is a matrix product formula. Let me explain this in this following way. If this I and J state are truly orthogonal, then the maximum inner product you can get is given by coefficient Fi is simply the inner overlap between A and state I. But now, since I and J do not necessarily to be orthogonal, so you need to pay a small rotation to compensate this effect. That is this IJ inverse. This I and J should be understood as a matrix with dimension L cross L and with summing over J. So that is the coefficient that maximizes the inner product between state A and this reconstruct state. But still, we don't know what's the value. I mean, we can only say that we succeed in reconstruct the state A if this your inner product equal to 1. That is, you reconstruct the fidelity of equal to 1. So how do we calculate that? So in the previous slides, we get that this maximum inner product is given by this formula. We have the overlap between A and I, and overlap between J and A, and then times this matrix inverse of overlap between state I and J. And we were going to use gravitational path integral to calculate this subject. The main difficulty is how to treat this matrix inversion 1 over ij. And of course, we were using replica trick. Let's denote this matrix as M. So we want to look at the matrix inverse, and we will the way we will take is to take m to the n power and take the limit of n goes to -1. So that's corresponding to the following gravitational path integral. Here we have, here I label I as I1 and J as IN plus 1. So we have in total n plus 2 boundaries. This is overlap between A and I. This is overlap between J and A. And in the middle, we have n copies of this of this matrix from I1 to I2 to IN plus 1. We will do the gravitation path integral with this following boundary condition and take the limit of n goes to -1. Since the state A is orthogonal to any other state of the I, so the only non-zero gravitational contribution is given by requires connected geometry between the first and last boundary. And then in the middle, you can have connected or disconnected geometries. Those all give you different non-zero answers. And if we look at the limit where the number of bases is much bigger than e to the s black hole, then only the fully connected geometry dominates, simply because you want the maximal index loop you can have. So with this, by disconnecting the geometry, the powers of L will decrease. And so in the limiter, if of L is much bigger than e to the s black hole, you only have this fully connected geometry dominates. And when you take the limit of n goes to -1, then you this fully connected geometry gives you the inner product of state A with itself. That is, this maximal inner product you can get is equal when L is much bigger than e to the s black hole is given is equal to 1. Therefore, you successfully reconstruct the state, and then A belongs. Therefore, we show that this A belongs to the span of this basis 1 to L. And in particular, in this proof, I didn't make a particular requirement on A. So any other state living on this brane is in this span. Is in this span. So in other words, this L state expands the complete Hilbert space of this black hole. A few comments. Here I show that we need to when L is much bigger than e to the s black hole, but the correct dimension actually should be given by e to the s black hole. That requires us to understand the phase. That's the same as understanding the phase transition of the page curve, basically, because you need to resum of all these Plana diagrams. And in this model, you can find that this fidelity just achieves 1 as long as L is equal to e to the s black hole. And that is also true in JT for a microcanonical black hole. The reason why you need to be microcanonical is because you just want to focusing on just the energy window. And there's no restriction on the choice of basis. So any e to the s black hole semi-classical orthogonal states can expand complete basis. So, so for example, you can consider about states where the basis expanded by like firewall excitations at the horizon. Or you can consider about those states with smooth horizon geometries and then different excitation at the interior. The claim is that you can choose any of those states to form a complete basis. And the third comment is about the remnant. So when we usually previously people argue there's a lot of issues with the remnant due to thermodynamic instabilities, because the remnant will have large entropy due to this large volume at the interior. But this analysis shows that actually the actual degree of freedom is much smaller. So we have both large spatial volume and a small degree of freedom. So that won't cause you any thermodynamic instability. And the fourth is we can extrapolate this result into the limit where the transverse area shrinks to 0. Then that will mean that all the different, the Hilbert space dimension of a closed universe is one-dimensional. Like all different excitations inside of the closed universe will be equivalent. Like any state I will be equivalent up to a phase, random phase. Here I'm drawing a cartoon.
Yeah. You mentioned that you can take the basis states to be firewall states, but if you want to take all the basis states to be firewall states, that choice is kind of measure 0. Do you agree?
I thought Marov and Pochinsky says that is measure
but
1.
It can be, yeah. I mean, it can be. I mean, it's at least I claim that
I'm leading this debate.
Okay. So you're not necessarily saying this. Okay, good.
Not
that's all right.
Use this firewall states.
Okay.
Okay, let me just to explain this cartoon a little bit. So imagine we are doing some gravitational path integral that only involve a closed universe. Because the closed universe does not contain any spatial boundary, and so we will only fix the initial condition that how we create this closed universe. That is labeled by this this red and blue dots. Those I'm imagining like different states creating different excitation inside of closed universe. Then you use gravitational rule to calculate the inner product between these two states. Then I'll choose this red and blue dots corresponding to different operator insertions in the closed universe. Then this inner product will be 0. But if you look at this, so that is like ij will be 0. But if you look at ij squared, then because you only specify the bounding conditions where you create this closed universe, but you do not there's no spatial boundary, so you do not specify what happened in the middle. So so that this inner product squared will give you a non-zero answer, and that's actually equal to I times j, because I just reshuffle this initial locations, and so this j, if you want to interpret it from quantum mechanics, then it will mean I and j actually are the same state, but with a random phase. Okay, so good. Okay, now I finished the first part. Sorry, actually the first and second part. Are there any questions? Okay, if not, then let me discuss this question. So when we're talking about the page curve and talking about this state reconstructions, we use those wormholes to do calculations. But are those wormholes real? Are those wormholes real? Like in some aspects, they are not real, since this replica system is like a mathematical trick. We first taking this n power and then take the limit of n goes to 1 or n goes to -1. So sounds like just a mathematical illusion, but in some aspects they are real. The first point I want to say is that the physical consequence of the wormholes are real. The entropy is the physical property, and the Hilbert space dimension is a physical property. And the second is that it can actually appear in physical process that involves scattering probability. So in the scattering probability in this model is just actually is very closely related to the second Renyi entropy in the purity calculation, because the scattering probability is given by the overlap between two states taken as squared. And if we choosing psi I and psi j to have different global symmetry charges, then then we will find that although the scattering amplitude psi I psi j is equal to 0, their probability will be non-zero. The scattering probability will be non-zero due to the existence of a wormhole. That is because when you have a wormhole connecting these two boundaries, these two copies can form a singlet. And okay, let me say it more clearly. So we can, in this model, we can assign this Endofwar brane have some ON symmetry. And then I and J can carry different symmetry charge. But then when we consider about on this wormhole geometry, this I can form a singlet. The, J and J can itself can form a singlet. And therefore, the global symmetry will not prohibit you to have a non-zero answer on this geometry. And so the fact that the gravitational path integral will give you a non-zero answer will mean that the global symmetry will be broken. On the other hand, gauge symmetry is preserved. That is because when you have a bulk gauge symmetry, then this will induce two global symmetries in the presence of two boundaries. Like you have a bulk gauge symmetry, and for the large gauge transformations, you have two large gauge transformations. One is vanish at the left-hand side boundary, one vanish at the right-hand side boundary. So these two large gauge transformations give you two global symmetries. Each forces each boundary to form a singlet. And that will make this wormhole contribution to be 0 if you have a gauge, if you couple the symmetry to be to a gauge field. Okay, so that this was this Endofwar brane model is kind of like artificial model. So in our paper, we discuss kind of a slightly more interesting model, but again, it's a UV complete model. So so naively you can think you can trust this for path integral, gravitational path integral. That is 2D gravity plus VKBF theory. You can take this 2D gravity to be the topological gravity or JT gravity, doesn't matter. In this VKBF theory, you have, okay, let me introduce the notation. You have a gauge field A that we take to be a U1 gauge field. And then you have a scalar field phi that is periodic. You can think about this as coming from a low energy limit from Higgsing a U1 gauge theory that carry charge K. And this theory have a global VK global symmetry that is shift this phi to be with a constant 2 pi over K. And that corresponding to this theory, they have K vortex configurations, and you can shift between these vortex configurations. And then you can look at like the transition probability between like one vortex to zero vortex. I mean that if you just look at one copy of the system, you look at e to the I expecting value of e to the I5, then that will give you a zero answer just due to this ZK global symmetry. But on this wormhole geometry, that is when you look at the transition probability, that give you e to the I5, e to the minus I5, and then this ZK global symmetry will this is neutral under the global symmetry, and doing the gravitation path integral give you some non-zero answer, and this is suppressed by e to the minus s, e to the minus n suppression due to this structure of the wormhole. So that's an explicit example how this works in other models. And so lastly, I want to okay, are there questions about this slide? No? Okay, lastly, I want to describe an ensemble average view of bulk, global, and gauge symmetry. If you think about gravity, semi-classical gravity, and describe ensemble, have a boundary view of ensemble theory, then we can try to understand what is the meaning of bulk global symmetry and bulk gauge symmetry. First, for bulk gauge symmetry, that is like a traditional rule of ADS-CFT. If we have some bulk gauge symmetry, then that will correspond to some boundary global symmetry. But the bulk global symmetry is unclear in the boundaries system. And here we can, in this ensemble average viewpoint, we can interpret the existence of bulk global symmetry as an emergent symmetry after ensemble average. In this BF theory model, 2D gravity plus BF theory model, we can see the following. First, this BF theory has a ZK gauge symmetry that will induce a boundary ZK global symmetry, and so that will mean that the Hamiltonian will be block diagonal in the representations, in the ZK representations. Here, 1 to k corresponding to the different representations of the ZK symmetry. And H1, H2 to HK have no relations; they can be different. But then if you do an ensemble average of this result, you need to choose a measure for this H1, H2, HK, and in particular, if the measure is invariant under the permutations between 1 and 2, permutation from 1 to k, then you induce emergent ZK symmetry. That is shift symmetry from the representation 1 to representation 2, and so on, I to I plus 1. So if you look at just a single if you look at some UV complete theory, then this new ZK symmetry is broken because all the H1 and H2 are different. But after ensemble average, those becomes equivalent. Therefore, when you just look at like a scattering amplitude, that will give you a zero answer. But if you look at more delicate quantity, like the scattering probability, then this answer will be non-zero. Another model is the SYK model, where in the boundary, yeah.
Can I just ask a question to see if I'm understanding? Let me posit an analogy, and you tell me if it's correct or at which point it becomes wrong. So your conclusion, I think, was that replica wormholes explain why there is no bulk global symmetry, or they're consistent with there not being any bulk global symmetries.
Yeah.
And so asking what good. And so similarly, I could have said replica wormholes explain why there's no information loss. They give me the page curve. So I guess the question analogous to the one you're asking on this slide would be, what's the boundary dual of information loss? What's the boundary dual of this fact that if I naively look at the bulk some other way, it looks like I am getting information loss. And I guess I would have said the answer is that if you average the out state over an ensemble, it's going to be a mixed state, and that's the sense in which information is lost. So is that sort of you're doing the analog of that for the global symmetry here? Is that right? You're trying to see how you can get the wrong answer from the boundary side.
Well, you put this way, but I was trying to put it another way. Like I trying to explain why you have this bulk global symmetry. How to see the bulk global symmetry from this boundary point of view. Like we don't know what's the boundary due of the bulk global symmetry. At least I wasn't taught in ADS-CFT.
And then let me backtrack for a moment. So suppose that I throw a bunch of protons or neutrons into a black hole, and I thought, let me, imagine that baryon number is a global symmetry. Then would you agree with the fact that that's going to be violated? So when the black hole is finished evaporating, I'm not going to get my protons and neutrons back. And moreover, would you agree with the fact that this can now be understood using replica wormholes?
I think that was understood at Hawking's time, just evaporating, right? Just ordinary Hawking evaporation. We don't know what is effective state, but we trust the Hawking's calculation. Here I'm talking about a slightly different scenario where it's the black hole is not evaporating. It's just a thermofield double. You're throwing baryon, and then you look at the probability to with a thermofield double with a like a lepton.
So what is the what are you getting out of the replica wormholes for the purposes of global symmetry? I think maybe I did not understand that correctly then.
Yeah. So okay. So first of all, this is like new scattering process that give you a violation of global symmetry. So Hawking's original calculation give you one particular process that have violation of global symmetry. You're throwing a lepton, and you're throwing a baryon, and then you let it evaporates, right? That is one situation. But here we are saying that by looking at scattering probability, there are new scattering channels that naively you thought you won't observe any violation of global symmetry. Because naively you will just look at the scattering amplitude, then you will find this scattering amplitude will be 0. But actually, if you look at the scattering probability, it will be non-zero. So you need to consider about more complicated object.
The probability for what will be non-zero?
Yeah, to non-zero. Yeah.
What will be non-zero? The probability for which thing will be non-zero?
Well, the transition probability between different charged states.
Right. So global symmetry will be violated.
Yes.
And so, but as you correctly pointed out, this was sort of expected anyway. So what is it that you're learning from the?
Well, I think okay. So I think it's like trying to build those old pictures in this more recent development, like how much of the previous stuff we can see from this replica wormholes. And here we see a explicit connection between the existence of replica wormhole and the violation of global symmetry.
Yeah,
no evaporation process is involved.
Yeah, but it's not that different, right? I mean, if it's just ascending into the horizon, interact with the black hole, and then that's just violate global symmetry. So in that sense,
well, in that sense, yeah,
different. Yeah,
it's also evolved black hole. So in that sense, it's not that different.
Yeah. But I think the point you're saying is that because those can be understood as ensemble average, I totally agree. I was saying coarse graining, but it's the same thing. It's ensemble average, and so you always break global symmetry in the sense that really scattering occurs. Yeah, but in order to understand the global symmetry at the level of amplitude, you could do that. You can take an ensemble at the quantum level, not like a mixture at the classical level. You do the quantum level, then it averages out to zero. I understand that. That's what it's saying. But then, is that true that that's not the consistent theory of quantum mechanics? Because amplitude is zero, still you have to get the probability to be non-zero. So that's not the quantum theory.
Wow.
So if you average a quantum theory, then you get the global symmetry only if you deviate from a consistent quantum theory at the boundary.
Yeah, well, you can say the following.
Okay.
But I think my hope will be the factorization issue will be solved. Then we will find that the scattering amplitude will also be non-zero.
Yes, that amplitude isn't non-zero for any microscopic theory.
For microscopic.
Yeah. Or if you do the ensemble after kind of square it, of course, that's a classical mixture.
Mm-hmm.
And because that's, and then what Replica Wormhole is doing, that it doesn't matter because for the square, it's giving a right answer. For non-square thing, it's just simply,
yeah, because the amplitude have this funny face, and
so it's not the right technique to see that kind of microscopic theory.
Yeah, the simple gravitational here I'm saying simple gravitational rule will not give you the microscopic scattering amplitude
because it's already coarse grain. Yeah, because it's already coarse grain.
Well, but okay. Well, at least I think. The idea that bulk global symmetry can be emergent from ensemble average of the boundary theory is like an interesting point to me.
Yeah, but it's in an inconsistent way. Is it true or not? Like from the boundary point of view, you have to inconsistent. Not I don't know. It's have to deviate from the standard quantum mechanical theory.
Well, I think if you just have like say N4 super Yang-Mills, then you won't find that there's a bulk global symmetry.
Yeah, because amplitude being zero and the scattering probability non-zero is clearly not what any quantum theory can reproduce.
Well, but you can put it another way. So like if you have giving you some bulk theory, you have some bulk theory that carries have some global symmetry, then you may ask. Then you may ask what will be the microscopic theory that will give you a factorization property. Then this will mean that the UV theory must requires a coupling that explicitly break this global symmetries. So in other words, this replica wormhole calculation will give you a lower bound on the strength of the coupling constant that breaks the global symmetry.
Okay, replica calculation give over, and that's of course I kind of agree. Yeah.
Okay, well, yeah, that's basically it. There's a future directions. Maybe we can discuss tomorrow. I mean, okay, I don't know much about like the microstate firewall puzzles. I mean, I don't know how to describe an infalling observer to test whether there is a firewall or not. But the papers I read are confuse me a lot. For example, some people say that the firewall states are like can form a complete like almost spans all the typical states. Therefore, you must be a firewall. But also maybe you can also say the other way. The non-firewall state can also expand the complete basis of the typical states. So how should I understand if I fall in a black hole in a typical state whether I should have a firewall or not? It's quite a puzzle for me, and but in particular in this in today's talk I was describing there's like a large redundancy of the semi-classical states. You can just pick any e to the s black hole state to form a complete basis. That is consistent. That is what semi-classical gravity tells you. So, but those states, so you can choose any particular basis, but those bases can have very different physical descriptions. So how do I understand if I'm an informing observer, like what experience should I experience? That is a big puzzle. And the second is about cosmology. So how do we understand that the Hilbert space dimension of a closed universe is one-dimensional? Like, okay, so this may be too speculative. If our universe also obeys this rule, then we will say that different initial state of our universe are actually equivalent. So we can start any initial state, but that may be too large a jump from what we have understand from black hole to our own cosmology.
Yeah, but because if you put the initial state, it's not closed universe. You're not treating as a closed universe.
Well, I mean, closed universe, I mean the boundary, there's no boundary in our universe.
Yeah, so therefore
there's no spatial
nothing
boundary
to specify. Everything is relational. It's just operator relation.
Yeah, well, but well, I think this is a stronger statement than the initial state of the universe need to satisfy the Wheeler-DeWitt equation, because the Wheeler-DeWitt equation can have a lot of solutions.
Yeah.
Here it's saying that all those solutions will be equivalent if you. But I don't know how to understand that. Okay, thank you.
Zhenbin. Questions?
This basis thing you said confusing. I don't know why it's confusing. I mean, of course, kind of opinion or whatever conclusion varies people to people, but at least it's not like, suppose typical state, black hole, not the firewall state, but you can have very special state to be a firewall state, and that can span the basis, right? It's like, if you think about the typical state, the entanglement entropy is like Page theorem. It goes like volume, but you can go to the basis, which is a product state basis. Oh, right. I mean, just spinning each up and down at each. That's a very specific basis, but in that basis, no entanglement at all. So it looks like all firewall, but you can make any typical, superposition of that. It's always you have generic entanglement, which is a maximum entanglement, which is a smooth geometry.
Yeah, so I don't know. Yeah, you have a basis of the firewall state. Why does it means that the informing observer will meet a firewall? That I don't know.
Okay, that's what you meant. Okay.
Yeah.
And then,
like,
yes, certain nonlinearity is needed. Yes.
For example, you can like think about a more physical situation. Here I'm talking about this stupid Endofwar brain model, but you can consider about some situation, more physical situation, where you just choose those just choose those states by like acting on operators at different times, at early or later. Then so if all the operators you acted are at early, then those so those I from 1 to L, those can be choosing to be L different L different states can correspond to insertion of operators at different early times. Like you have like 1 thermal times earlier or 2 thermal times earlier to L thermal times earlier. So this I could be those states. So we will say that those early insertion of operator states will span the Hilbert space. But for observer falling in at this time, those will not this observer will not meet those energies. So this is like not a firewall state for this observer. But on the other hand, those I states can also be like this basis of states can also be like creating inserting operators at later times, like 1 thermal time later and 2 thermal time later and L thermal time later. And those will also expand the complete basis. And for an informing observer, all of those states he will meet this shock wave. He will meet that firewall. So in that basis, like this observer will just in every basis of state, this observer will die.
Yeah.
Because of high energy correlation. So how do I understand this tension between these two?
Yeah. So like this state dependent thing is that if you take a superposition of those firewall states, the typical state, then the right operator you have to use to describe the observation of falling die is the one which allows you to interpret, smooth Hamiltonian, and so of course then why that's the right operator to describe observable? Of course, people didn't prove it.
Raphael says that there will be the frozen vacuum problem.
No, not necessary.
Okay, you guys.
Anyway, those would be become forever. So I think.
I don't know, but
yeah, I will stop.
What I know is if you give me a boundary operator to tell me that this describe an informing observer, then maybe I can do a calculation to test whether there's some like a yes or no. Like maybe a good question is like, is the firewall ensemble average result? Is the existence of a firewall is a ensemble average, like self-average result?
No, it's just very special state to me, but.
Okay, thank you.
We don't really know very well what the gravitational path integral is good at doing. It's a lot more powerful than we think, but that clearly there are some applications where it gives us the answers we don't want, like information loss.
Yeah.
And then we use it differently. It gives us the page curve. I think it's a little bit related to the fact that more generally in quantum mechanics, you can if you have more than one copy of a system, you can learn things from relatively simple operations that otherwise would be extremely difficult.
Yes,
so for example, the scattering matrix is very hard to calculate. So if you wanted to check directly the purity of an out state, you'd have to know what the scattering operator is, predict the out state, and then measure in that basis that includes that state, which is like a super hard thing to do at every level. But if you have two copies, and I'm not talking about black holes necessarily, but anything, right? If you have two copies and you just send two copies of the in state in, you make two of whatever, hot pieces of coal or black holes, and you just want to know if the out state is pure or not, then you don't need anything else. You don't even, you can just do the swap test and you and I think that the gravitational path integral is a little bit like that. It seems to be good at doing the simple things. And so if you ask it questions that are sort of equivalent to asking the swap test question and not the compute the exact out state question, then it succeeds. And I just don't think we know how to put the firewall question into a simple category yet.
I thought it's a yes or no question, right? Yes, the question is whether this informing observer die or meet or doesn't meet a firewall. So it's a yes or no question. So
yeah, it's a yes or no question, but it's
so
yeah,
that will be naively it will be a semi-classical gravitational calculation can give you if you allow multiple copy.
Yeah, I would argue that it's a yes or no question, which is very closely tied to the question of computing the density operator, though. Which is, so if you believe Hawking's calculation, there's no firewall, but you also get the wrong answer for the density operator. But that, yes. I don't, maybe there's a different calculation we can do, which gives us a different answer. but you want a calculation that both tells you that you're not losing information and that the horizon is smooth, and that seems still unknown how to even make that logically possible, I think. But
well, if you accept that the different states are not orthogonal, then you don't, right? You don't have this issue.
No, I don't think so, because I'm just making the trivial statement that if you assume the vacuum at the horizon, then half of the vacuum is a mixed state. I'm not.
That doesn't mean.
So for example, I could imagine that maybe more sophisticated calculations could give us still further evidence of purity or of unitarity. but I don't see how they can address that issue. Or to put it differently, I think the ideas that people have put forward, ER equals EPR, the kind of things that whatever, Steve Giddings had ideas, Yasunori had some ideas. All of those are ideas that speak to this issue of getting rid of the firewall. And as far as I can see, the Yasunori may not agree, I don't know. They all involve additional elements which are still necessary, even now that we understand all the wonderful things that replica wormholes can do. There's still ingredients there that, or to put it differently, I don't see these ingredients coming out of the replica wormhole.
Oh, no, I agree. In fact, that's like what's the good observable to choose. For example, what I showed was the existence of operator, which describe interior, and the existence of corresponding to Hamiltonian. Why that's the right observable? But the operator, if you have a state feasible space of dimension n, you have n square operator, or 2 times n square operator, that you can do anything. So what's the right good observable? And existence of locally looking observable looks, because we know it's local, then it looks like classical, you can organize observation in that way. That part is a kind of guess or like empirical, but so only thing it was shown is the existence of those operators. And then you're right, you need some, what's the measurement, what's the, what's a good operator to use.
Any non-firewall related questions?
Yeah, great point. Agree.
I apologize for this, for bringing it up.
It always gets
you need a big apology for bringing that here.
Well, if not, then let's thank Zhenbin again, and I guess we'll see him tomorrow at the meeting.
Thank you.
Thank you.
Thank you, Zhenbin.
You.
Thank you.